This is the course of 200 DF English of June 4th, H9H10. So last week, not last week, 2 weeks ago, because with you we lost a week due to Ascension. Last week we gave a look at the various mechanisms for heat conduction, for heat propagation, conduction, convection, and radiation. Today I want to do two things. The first thing is to look at dilations, and the second thing is to look at the law of perfect gases, which is these things which maybe you saw already in chemistry also. I don't know, did you do that in chemistry? Doesn't ring a bell? Okay. Well, let's start with dilation, okay? You remember maybe that heat causes, if temperature increases, it causes the thermal vibrations inside the material to increase, okay? So imagine a material made out of atoms, and these atoms, if you heat up the material, they are going to vibrate more around their stable positions. And in vibrating, so they are going to interact a bit within each other. And the effect of that is going to be to push back the atoms, to make the atoms a bit further away from each other than they were. And so if you take a piece of metal like that at some temperature, and you heat it up at a temperature which is higher than the initial temperature, what you will observe is an increase in length. Okay, if I take a long piece of metal, a wire of metal, I warm it up, this wire is going to get too long. It's going to get longer. In some cases, it's too long. For instance, you have an illustration of that in the summer. Sometimes in the summer, when the weather is very warm, the trains can no longer run. Or this happens in France pretty often with the TGV, which is a very fast train, so it has more constraints. And you know, if you have a train line, okay, let's assume that this is a train line, and you have the cables distributing the current, which are running above the train line, okay? These are poles, and you have the cables, and then when you have a train, here you have a device which makes contact with the cables, and this is how the trains receive electricity. Okay. Now, in the summer, when the temperature is very warm, these cables, they become longer. Okay, they dilate according to the rule I just explained you. So if I exaggerate that, the cables are going to be longer and they are going to come down further. And in some cases, when the temperature is really high, these cables are going to be so long that they come down too low, and so it's dangerous to have a train running, especially a TGV at high speed, because it could cause accidents with these cables which are not tense enough. Okay, so this is why sometimes in the summer the velocity of TGVs is reduced, or even in some cases the trains cannot run. Okay, we have another phenomenon in trains which is important in the summer. You know that the trains, they run on rails, so I'm trying to draw a rail here, okay, and the rails, they are long pieces of metal. So with the raise in temperature, they also increase in length, right? This is why when you build a train line, you never put the rails that touch each other. You need to leave some space between the rails. It's going to be a few centimeters, but you need to leave some space between the rails so that if the temperature increases, these rails, they have space to expand. Okay? And so this separation between the rails is of course bigger in the winter than in the summer. And this is why in the winter, if you listen to the tick, 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 tick of the trains, it's going to be much stronger than in the summer, because this tick, tick is caused by the wheel passing between two rails. And if the hole is bigger, it's going to make more noise. Who is currently eating his microphone? A microphone is not something you are supposed to massage and to sit on when you're using it, otherwise it's a mess, okay? So we have lots of phenomena which are connected in everyday life to this capacity that materials have to expand and contract with temperature. Another example which I gave in the course is this. Look at the image on the course. Do you see what this is? Do you understand what this is? This is a bridge. This is the beginning of a bridge. And the bridge, it's a long piece of concrete and metal. So the bridge also expands and contracts with temperature. Okay, so when the temperature is high, the bridge is a bit longer. When the temperature is low, the bridge is a bit shorter. And if you don't want the road next to the bridge to be completely broken and teared apart, then you need to add a space at the end of the bridge for this dilation of the bridge or contraction to be absorbed. And this is such an example. Okay, here you have the normal road on one side, on the other side you have the bridge, and then you have this structure which can move. The bridge can I mean, these triangles here, they go one into each other when the bridge is longer, and they separate from each other when the bridge is shorter in the winter, okay? If you pass on the Pont du Mont Blanc, you will see this very clearly on the two sides of the bridge, okay? It's not exactly the same design, it's a bit different, but it's exactly the same principle. And you have that on all the bridges. If you don't do that, it can be that your bridge breaks when it gets too long or too short. Okay? Are you still with me? Good. So the physics of dilations is not an extremely interesting physics. The formulas we have, they are formulas which we extract from experiments, okay? And the way we build these formulas, this is for the linear dilation. So you take a piece of metal, let's say a piece of whatever, it has a certain length L initially, and if you heat it up, its length is going to increase by some delta L, which is a small portion of L, okay? And you compute this delta L in the following way. The delta L is of course proportional to the initial length of the sample, okay? The longer it is, the more it will expand, because each length of the piece extends, and so if you have more pieces together, if the piece is longer, it's going to extend more. So the delta L is proportional to L, is proportional to the temperature difference, and be careful, the delta T is always final temperature minus initial temperature, so this delta T can be positive if the temperature increases. It can also be negative if the temperature decreases, okay? In this case, the delta L is negative, and you have a contraction, not a dilation. And then here there is a coefficient which is determined experimentally. So each material has a different coefficient, and we are going to do calculations in a moment and look in the table what these coefficients are, and we are going to do some calculations, okay? That was for linear dilation. That was for the dilation of one object which is long, like a piece of wire, a piece of cable, a stick of metal. Now, if you have a piece of material which is bigger than that, which is not only long, but which could be a volume with a certain width, a certain height, a certain length, then you can be interested in the variation of the volume. Okay, so we have a formula for that. You see, it's exactly the same type of formula. The change in volume is proportional to the initial volume itself, to the temperature difference, and here to a coefficient which we call gamma, and gamma is just 3 times the value of the alpha. So the coefficients for volume dilation is just 3 times the coefficient for linear dilation. Okay. That's why I'm telling you it's not an extremely interesting physics, but it has important consequences for everyday life. So this is why I'm telling you about. That was for solids. Solids can be long or they can have a definite shape. And so you need linear dilation and volume dilation to describe the dilation of solids. Now, of course, in the liquids, it doesn't make much sense to talk about the linear dilation of a liquid. A liquid is not like a cable. Okay, for a liquid, we just have volume dilation. We just define volume dilation. And the coefficient here, gamma, is generally 10 to 100 times larger than that of solids. Okay, so it means that liquids, they expand and contract with temperature more than solids do. Okay. Okay, so again, these coefficients, we will find them in the tables. We will see that for the various liquids. And then for gases, we have again the same law. Again, for gases, we don't talk about linear dilation because it doesn't make sense. We talk about volume dilation. We have, so the delta V is proportional to V and the temperature difference, and a coefficient gamma, which is not the same as the other one. But this coefficient gamma has the same value for all the gases. Okay. How can you understand that it has the same value of all the gases? Well, a gas basically is what? A gas is an assembly of molecules which move in all directions and they undergo shocks with each other. Okay? And so this mechanism is independent of what kind of molecules you have. Okay? This is the reason why most gases behave in the same way if you are at a temperature and at a pressure which are not completely crazy, extreme. Okay, if you are at around the normal pressure, the atmospheric pressure, and around the room temperature of 20 degrees, I mean in this area, then all the gases will expand in the same way with the same coefficient, which is 1 over 273 Kelvin minus 1. Okay? So that was the theory. Now let's do some problems. Okay? A rail made of iron is exactly 100 meters long at 10 degrees. How long is it at 35 degrees? What can you conclude about how to build railways? Okay. You want to try to do it or we do it together? Together, please. Okay, I was expecting that. So it's a rail, so it's a long piece of metal. So we are going to use linear dilation, right? What we're interested in is in knowing how much longer the rail will be. So we are going to compute the delta L, the changing length, and we saw that this delta L is given by alpha times L times delta T. This is the law we saw 1 minute ago. Now this alpha is the alpha for iron. So if we want the value of this alpha, we need to use the table. Okay? And we are going to use the table always in that same place, which is very important, is these central pages where you have the properties of all materials. Right? So if you have your table, take it, otherwise look at mine. So I'm looking for iron, so I have to look in French for F, okay? Iron is here. Sorry, here, fer, okay? And then here, am I at the right page? No, I'm not at the right page, because here we have the fusion and temperature, we have the latent heat, we have the specific heat, so it's not the right page. So we should go back one page, because there are 4 pages for each list of elements. And here you have iron, you have the specific mass, and then you have this thing here. You see coefficient de dilatation, linéique. So this is the linear dilation coefficient. This is what we call alpha. And this is the volume coefficient, the gamma. Okay? So what we need is the alpha for the iron, and the alpha for the iron, you see it here, it's 12 times 10 to the minus 6 inverse kelvins. The unit is here. Okay? 12 times 10 to the minus 6, right? So now I'm going to compute that. So it's 12 times 10 to the minus 6, the value for alpha, times the length. Well, the length is 100 meters, and times the delta T. The delta T is the final temperature, 35 degrees, minus the initial temperature, 10 degrees. Okay, at 10 degrees, the length was L. Now we are computing the length at 35 degrees. And this is the law we need to apply, right? So this is now 12 times 10 to the minus 6 times 100. It's 10 to the minus 4 times 35 minus 10, 25. So how much is that? Let me take my phone. So it's 12 times 25 divided by 10,000, and this gives me 0.03. What unit is that, in your opinion? Hello, hello? What unit is that? Huh? It's, come on, it's a length different. What unit can it be? It's meters. It's meters, okay? It's a length. And here, if you look at the units of these people, alpha is in 1 over Kelvin, okay? The length is in meter, and the temperature, you can say it's in Kelvin or in centigrades, okay? It's the same because we have a delta T, okay? So you see that the Kelvins here and here cancel, and you are left with meters, which is okay, right? So 0.03 meters, how many centimeters is that? Haha, it's 3 centimeters, okay? So from 10 to 35 degrees, a rail which is 100 meters long will change its length by 3 centimeters, okay? And this is, well, maybe 100 meters for a rail, it's a bit long. Real rails, they're a bit shorter, okay? But even if you took rails which are 100 meters long and you put them during the winter when they are short, you need to make sure that they have enough space to expand during the summer, because if you don't give them the space to expand, they will start becoming tordu. How do you say tordu in English? I don't know. Okay, so you need to leave this space for the rails to expand. So you need to know that when you build train lines. Okay, if you don't take that into account, your train line is going to be destroyed the first summer. Okay, good. Second exercise, we measure the length of an object made of an unknown metal at 20 degrees. The length is 1 meter. Okay, so the initial length is 1.000 meters. We then heat up this object to 60 degrees. So at 20 degrees, we have 1 meter. We heat it up at 60 degrees, and we measure a length of 1.001 meters. Okay, so from 20 to 60 degrees, the length has increased by 1,000th. Okay, and now the question is, what is the coefficient of linear dilation? Okay, so how do you think we are going to do that? Hmm? So one of you wants to do it, or should I do it? Hello, hello? Yeah, I should do it. God, you're exhausted. Poor people. Okay, the law is the same. The law we use is exactly the same as before because we are again looking at the linear dilation of a long object. Okay? Now this delta L, what would you put for delta L? Delta L is going to be the final length minus the initial length. Okay, there is a difference between these two of 0.001 meters. Okay, so our delta L is going to be 0.001 meters. This is the change in length. The delta T, what would it be? They participate a bit. The delta T, it's the final temperature minus the initial temperature, 60 minus 20. L, the initial length, is given here, it's 1 meter. Okay, and alpha is what you are trying to determine. So what do you do now? Hello, hello? Yeah, so you isolate alpha. Okay, so you have to divide by L delta T on the two sides. So it's going to be L divided by L delta T. Right? So let's put in the numbers. Delta L, we said it's 0.001 meters. Okay? L is 1 meter and delta T is 60 minus 20. It's 40. Right? So I found now a coefficient 0.001 divided by 40, and this is 2.5 times 10 to the minus 5. Okay? And what is the unit of that? You remember? We discussed it before. The unit of that? Unit of alpha is Kelvin minus 1. Inverse Kelvin. 1 over Kelvin. Okay? Because here we have meters, here we have meters, here we have Kelvin, so we need to compensate for this Kelvin. So alpha has a coefficient of as a unit of Kelvin to the power minus 1, right? We could even play now and try to determine which substance this is. Unknown metal. Aha, yeah, let's see. Can you spot a possible material with these properties? So let's look at the table, okay? And let's take this column, coefficient de dilatation. We determine the linear coefficient, and we are looking for something which is 2.5 times 10 to the minus 5. So here we have something which is close, but it's alcohol. No, it's aluminium, 2.3 times 10 to the minus 5. So that could be a possibility. Then what else do we have? We have 15 times 10 to the minus 5, 16, 20, 12, 9. Yeah, so let's see a few pages further with the other substances. Well, I already did that exercise. 25 times 10 to the minus 6, which is equal to 2.5 times 10 to the minus 5. So this is magnesium. Magnesium. Have you seen magnesium, metallic magnesium before? I will show you. This is, whoa, this is my previous computer. It's made of magnesium. It was a very nice computer. I regret it a lot. The new one I bought is not half as nice as it. You see, all these metallic parts of the computer, they are made out of magnesium. And this has the advantage of being, well, let me show me, okay? This has the advantage of being extremely light. It's lighter than aluminum, and it's strong, okay? So magnesium is a metal. It's not very often used, but it's a metal. And the way maybe you heard about magnesium, there's a food supplement. Okay, you know that some people lack magnesium. You know what the symptoms are? It's a very common problem, the lack of magnesium, because modern food does not contain enough magnesium, because magnesium, you find it maybe mainly in raw cereals. So if you eat white bread, you don't have magnesium. If you eat black bread, you have magnesium, okay? And you know what the lack of magnesium causes you as symptoms? You have no idea? This is, sorry? Excuse me? You what? I didn't understand. You faint. I don't know if you faint when you lack a lot of magnesium, but the first symptoms of the lack of magnesium is you go to bed in the evening, you try to sleep, and you cannot sleep in because your legs are kind of shaking a bit. They are kind of tickling inside, okay? It's called restless legs syndrome. And this can be very efficiently addressed by taking magnesium supplements, which you can buy freely even at Migros. You don't even need to go to a pharmacy. So magnesium, especially in the times of nervous stress like exams, etc., you may well have a lack of magnesium. So take some magnesium from time to time, or if you don't want to take magnesium, eat apples or apple juice because it contains a lot of magnesium. Okay, let me stop talking about magnesium. What is the volume of oil which, when getting heated from 20 to 100 degrees, see its volume increase by 1 cubic centimeter? Aha. So, how do we do that? It's volume dilation, and it's oil, so it's a volume dilation of a liquid, okay? The volume dilation of the liquid is expressed in this way, okay? The volume dilation is given by the initial volume, the temperature difference, times a coefficient which I think we called gamma. Is this correct? Yes, gamma V delta T, okay? And the value for this gamma, we should find it in the table because we don't have it here. It says oil, so we will look for the gamma of oil, okay? Then we would like to determine what? We would like to determine the volume increase. So the volume increase will be given by what in this equation? Where's the volume increase in here? How do we call it? Delta V. Okay, the volume increase is delta V. When getting heated from 20 to 100, this means the delta T is final temperature 100 minus initial temperature 20. Okay? And then the gamma, we need to look for it in the tables. So let's look for huile. Huile hydrogène, it's on the previous page. So now we have a little problem here because we have huile d'arachide, de chauffage, d'olive et transmission de chaleur. Stop hitting the microphone. You have a microphone on the table or what? Okay. You see here we have no values for the other types of oil. The only type of oil for which we have a value is the heat transmission oil, which is fine. So let's take this value. It's 7 times 10 to the minus 4. Okay. Well, you don't see it well, but it's here. Okay. Oops. 7 times 10 to the minus 4. Okay, so this gamma is 7 times 10 to the minus 4. right? The delta V, we said it's 1 cubic centimeter. Can I go on and do my calculation like that, or there is some problem with the units? What would you do? What if I leave my delta V in this way? What is the computation? Because what I need to calculate now is V, okay? What is the volume of oil which, when getting heated from 2200, sees its volume increase by 1 cubic centimeter? I can transform this in meters if I want to be a good boy, but it's not really helpful. Because if you leave the delta V in cubic centimeters, you will have the V in cubic centimeters. And then if you want, you can transform it, okay? You don't need to do this twice, okay? So let's leave all this in cubic centimeters, and now we need to express the V as a function of the rest, okay? So we need to divide by gamma delta T, so the volume is going to be delta V divided by gamma delta T. The delta V is 1 cubic centimeter. I write the unit here so that I don't forget it, because it's not cubic meters, now it's cubic centimeters. And down here we have 7 by 10 to the minus 4, and we have delta T, which is 100 minus 20, which is 80, okay? Let's see how much this is giving us. Okay, it's going to give us a big number, of course, because if you want to have 1 cubic centimeter of expansion, you need a volume which is much bigger than that. So we have 1 divided by 7 times 10 to the minus 4 times 80, and this gives 17.85 cubic centimeters. That sounds like a lot. No, I think it's okay. Did I do something wrong? Seven times 10 to the minus 4 times 80, 1 over x. It's okay. It's correct. Okay? So you see, if you have a volume of 17 cubic centimeters of oil, then when you heat up the oil from 20 to 100 degrees, you will see a volume increase of 1 cubic centimeter. This is something you could even observe in a pan. So if you don't believe me, which you're welcome to do the experiment. Take a quantity of oil, put it in a pile, in a pan at room temperature, mark with a marker the level of the liquid, heat it up, and normally you should see an increase in volume. Okay? Magnifique. Now we come to the last chapter, and after that I will let you rest, which is the ideal fluids or ideal gases. Ideal fluids, ideal gases comes from the same idea I told you before. When you have a gas, you have essentially particles which are unconnected, they are not linked to each other, and they just travel, okay, with certain velocities, okay, and they travel in all directions at velocities which can be very high. I mean, the velocities can be typically a few hundred meters per second, okay, it's fast, okay, and these molecules of gas, they undergo shocks and they behave in different ways, but all the gases share the same property. What the molecules themselves are made of doesn't matter so much. And so this is why you see behaviors in gases which are similar, independently of the type of gas, and if you don't go to too high pressures or too high or low temperatures. Okay? And there's a number of laws that you can see. Okay? And there will be laws between three very important parameters for a gas, which are the pressure, the volume, and the temperature. Okay? Now we are discussing about the dependency of these variables between themselves, P, V, and T. And a number of people, especially that was the 19th century, a lot of people have studied that and they have come up with partial laws. But it's nice to see these partial laws. One of these, when I say partial law, I mean it involves only two of these quantities and then only two of either P, V, or T. And then when we will have seen partial laws, we will soon see the complete law. So Charles is an English guy. He observed that the volume divided by the temperature is constant. How should you understand that? Well, you take, let's say, a syringe, okay? And inside that syringe, you have a certain volume of a gas at a certain temperature. Now, if the temperature increases, what's going to happen, in your opinion? Assuming you are still here, because I no longer hear you. If I sorry, the what? The velocity becomes bigger, so the pressure increases actually, and these particles which are moving around in the gas, they will hit with more energy the piston here of the syringe, and what is going to happen is that your syringe is going to expand, okay, and the gas is going to take more space when you have a temperature which has increased. Okay, you can take a syringe, you can do it. I don't have a syringe here. You can take a syringe, you put it in water, you heat it up, you will see that the syringe, the piston will go back, and then if you put it back into cold water, the piston will come down again. Okay, so there is a relationship between volume and temperature. When temperature increases, volume increases. When temperature decreases, volume decreases. Right? And so this is done at constant P. So it means the pressure inside the gas here is the same as the pressure inside the gas here. Of course, the pressure will increase a bit to push the piston, but then the piston will stabilize at the same pressure. Okay? Good. Second law, Gay-Lussac law. Gay-Lussac was a French guy. Here he considers P and T, and he keeps the volume constant. Okay? If you keep the volume constant and you increase the temperature, what's going to happen? The pressure is going to increase. Why? I don't know if you understand that. Okay? Why is that? Well, let's imagine we have a constant volume. Okay, so the volume is the same. Well, on my drawing it's not the same, but let's say it's the same. The volume is the same in the two situations. Okay, in the first situation you have a pressure P1. In the second situation you have a pressure P2, which is higher than P1. Okay, and here you have a temperature T1, and here you have a temperature T2, which is higher than T1. So how does an increase in temperature influence the pressure? This is, if it's not clear for you, don't worry. It's normal that it's not clear. Because when we studied pressure, there is an interpretation of pressure which I didn't tell you about. It's the microscopic interpretation of pressure. Actually, where does pressure come from? Okay, let's suppose that here we have a piston and we have here some gas at a pressure P. Okay, the particle of the gas, they are going to move. They move at pretty high speeds, and they are going to undergo shocks with the piston. Okay, and they are going to be pushed back by the piston. Okay, and they are going to undergo these shocks all around the surface of the piston. But these shocks, they tend to push the piston up. And this is actually the microscopic interpretation of pressure. When you have a gas with atoms moving at a certain velocity due to thermal agitation, the molecules of the gas, they hit the walls of the container, and this constant hitting of the walls by particles, by molecules which go at a certain speed, this is what produces pressure at a microscopic scale. Okay, so now you can understand that if you increase temperature, you increase pressure, because when you increase temperature, you increase the thermal agitation, so you increase the speed at which these molecules are going to hit the piston. And if they hit the piston faster, they're going to push the piston more, and so this gives you an effect on pressure. Okay? Are you following me? Good. Third law, it's the Boyle-Mariotte law. So this was Gay-Lussac, P over T is equal to constant. The Boyle-Mariotte law is P times V is equal to constant. It's no longer one thing over another. It's one thing times another. When you have V over T, which is a constant, it means that if V increases, T has to increase too, so that the value of the fraction remains the same. Here, when T increases, P increases, and conversely. Okay, but here this is a different law. It's P times V, which has to be a constant, which means that if P increases, the volume decreases, and if P decreases, the volume increases, so that the product can remain a constant, right? And this is something you can understand pretty well. If you take a certain volume of a gas, and you decrease this volume, so you compress it, you're going to increase the pressure inside. And if you increase the volume, you will give more space to the gas, so the pressure will decrease. Right? Hello? Okay. So now these three laws, which have only a historical interest, these three laws, you can summarize them by one law, which I wrote here in a very simple way, and then I will show you a more educated way to write it. Now you can say, based on these different laws, that P times V over T is a constant, because we know that P over T is a constant, we know that V over T is a constant, and we know that P times V is a constant. So in the end, the product of pressure, volume, and temperature for a system has to be preserved during a transformation. Okay, so if you have initially a situation with volume P, with pressure P1, volume V1, temperature T1, you do a transformation, you get another state with a pressure P2, a volume V2, a temperature T2. Well, P1 V1 over T1 has to be equal to P2 V2 over T2, because this object is constant. Okay, and this allows us to compute a certain number of things, which we are going to do in a moment. Now, I told you that this law is written in a very basic way, but if you look for this law in the books, it's written usually in another way. It's written like this. So the constant, before I said that PV over T is equal to constant. Yeah, actually this constant has a certain value. This constant is equal to N, the number of moles, times R, which is a constant, and the value of R is this, 8.31. Okay, so the relationship between the pressure, the volume, and the temperature obeys this equation, which is a very important equation. This is very important. And the constant is here expressed in physical terms. It's the number of moles times the constant R, which is worth 831. Okay, and this is called the ideal gas law, la loi des gaz parfaits in French, and it's an important law. Okay, so we are going to do 3 exercises with that law, and then it will be over. Let's start with this. A gas occupies a volume of 1 cubic meter at 15 degrees. The same gas occupies a volume of 1.1 cubic meter at an unknown temperature T. What is the temperature? This one we will do together. The next one you will do it by yourself. Okay? As I said, we have a situation 1 and a situation 2. Okay? Situation 1 is the initial situation. So the volume initially is 1 cubic meter. So let's write V1 is 1 cubic meter. Okay? This 1 cubic meter, we have it as a volume when the temperature is 15 degrees. T1 is equal to 15 degrees. And then V1, T1, P1, we don't know P1. But we will see that. Now, situation 2. The volume V2 is 1.1 cubic meters, so it has increased by 10%. Okay, and the temperature T2 is unknown, right? And the pressure we don't know, but since they don't talk about the pressure, we suppose that the pressure P2 is equal to the pressure P1. So in this specific problem, we work at constant pressure, okay? So what can we do? We can use this law, but it's complicated because here we have nothing to compute the number of moles. Or we can use the simplified form of the law, where we say that PV over T is a constant. And if PV over T is a constant, it means that P1 V1 over T1 has to be equal to P2 V2 over T2. Okay? You see the strategy to solve that. Right? We use the fact that this thing is a constant, and so it has to have the same values before and after the transformation. Now we said the pressure doesn't change. Pressure doesn't change. P2 is equal to P1, so we can cancel the pressure from the equation. And now what would you do to determine the temperature T2? Now you know how to do that. Yes, please. Exactly. Okay, so you do a cross product. V1 T2 equals to T1 V2. And so this tells you that T2 is going to be V2 over V1 times T1. Okay, and so V2 over V1 is 1.1 divided by 1. 1.1 divided by 1 is, of course, equal to 1.1 times T1, which was 15 degrees. What do you think about that? Should we use degrees here? Centigrades? This is the big difference between what we do now and what we did before. Before, we were always considering temperature differences. We had this delta T. Okay, so delta T, it's T2 minus T1. If you take the difference in centigrades, it's going to be exactly the same as the difference in kelvins. But in these laws here, we don't have temperature differences. We have temperatures. And so we need to use the physical temperatures. If you do these computations with the centigrade degrees, it's going to be totally wrong. Okay, because the centigrade degrees, they become 0 at 0 degrees because that's where water freezes. But here we are dealing with a gas which occupies a certain volume. This has nothing to do with water. And so we should not take a temperature scale which is based on water. We should take the absolute temperature scale, which starts at the absolute 0. Okay, so all these temperatures, we need to write them in kelvins. Okay, so 15 degrees, can you tell me in kelvins how much it is? Hello, hello. Why is it so silent? Open your microphones. I'm not going to eat you. Huh? Are you there? Oh God, did I disconnect? No, you are still here. Why don't you talk? You don't hear me? Ah, so you're just lazy. Huh? Yeah, we have to add 273 because the absolute zero is at minus 273.15, but you can forget about the 0.15. So T1 is 273 plus 15. So 283, 288 Kelvin. Okay? And so here I need to put 288 Kelvin, and the answer will also be in Kelvin. And if I wanted the answer, oh, sorry, I'm not showing you my page. And if we want the answer to be in Celsius, we need to transform it again. So 288 times 1.1, it's 316. 316.8 Kelvin. And 316.8 Kelvin, if you do minus 273, it's going to be 43.8 Celsius. Okay? And the result is going to be completely different if you do it with Celsius degrees. If here you had put T1 15 degrees, okay, and then you do 1.1 times 15, you get 16.5. And sorry, but going from 15 degrees to 16.5 degrees, it's absolutely impossible that it causes a dilation by 10% because this is a very small temperature difference. But you see here, if you use the kelvins, then it tells you that if you want the volume of your gas to increase by 10%, then you need to go from 15 degrees to 43.8 degrees, and this is acceptable, okay? Whereas 16.5 was not. Okay? Yes. Ah, good. Okay, let's do one more because I have the impression that you are tired. Your tires contain air at a pressure of 2.6 bar. Okay, the pressure in a tire is approximately 2.6 bars. Why do we need pressure in a car tire? Do you know that? Do you have an idea? Why do we need to have such a high pressure in a car tire? Parce qu'il y a des explosions pour faire avancer la voiture. Attends, tu sors ça d'où? Les pneus, ils explosent pas pendant que la voiture, elle tourne. LOL! Oh là 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 là, la mécanique, c'est pas ton truc, on dirait. Non, les pistons, ils sont dans le moteur. Les pistons, ils font bouger le moteur. C'est ce qui fait tourner le moteur, et le moteur, il fait tourner les roues. Ok, mais les roues, elles explosent pas. Why do you make me speak French now? Okay, but on each one of the wheels, you have the weight of the car. Okay, if this is a wheel, this wheel carries the weight of the car, and we have 4 wheels, so if your car is 2 tons, each wheel is going to carry a gravitational force of 500 kilos times 10, 5,000 newtons. Okay, and if you want to hold this weight with your tire, you need here in the place where your tire touches the road to have a certain pressure to produce a force which is going to compensate for this gravitational force and hold your car up. Okay, so here you have a force which is pressure times surface, and this force is what your tire needs to hold the weight of the car. Okay, so the tires, they are inflated because they hold the weight of the car. Okay, whatever. You have a pressure of 2.6 bar, which is 260,000 Pascal inside the tire, at a temperature of 20 degrees. After driving on the highway, the tires reach a temperature of 40 degrees, so 50 degrees. So T2 is 50 degrees. You understand why the tires get warm when you drive? You have any idea? What could that be? Usually when something produces heat, it's because there is friction. Okay? So the tires, they undergo friction with the road and deformations because the tire, when it touches the road, on the side where it touches the road, it's a bit squeezed. So the squeezing changes the structure of the tire and also causes the tire to heat up. So when you have driven for a certain time, for a few hours, fast on the highway, maybe in the summer, then your tire can reach, the air inside your tires can reach a higher temperature, and therefore the pressure of the tire is going to increase. Okay? So if you want to use the law, you have P1 V1 over T1 is P2 V2 over T2. But now what is constant here? Okay, which one of these parameters is constant? Pressure, volume, or temperature? The volume, right. The volume. The tires, they don't really get bigger, okay? Because the tire, they have a structure out of steel which keeps their diameter fixed. Okay, these are not like balloons, the tires. They have a fixed size. Okay, so the volume is constant, but now we have this equation P1 over T1 is equal to P2 over T2, and we want to determine P2. Okay, so P2 is going to be T2 over T1, T2 over T1 times P1. And now the temperatures, ladies and gentlemen, we must absolutely put them in kelvins. Okay, so let's compute 20 degrees centigrade. It's how many kelvins? I recall you the scales. You have the Kelvin scale, which starts at 0, becomes 273 when the centigrade scale is 0, and here we have minus 273. Okay, so 0 degrees centigrade is 273 Kelvin, and so 20 degrees centigrade is going to be just 293 degrees Kelvin. Okay, so here I have T2, which is 293 degrees Kelvin. I have P1, which is 2.6 bar. I can leave it in bar because so I'm going to have a result in bar. That's fine. And T1, oh, sorry. I said something terribly wrong. It's T1, which is 293, and T2, it's 273 plus 50, so it's going to be 323. Okay? And so now we can compute the final result, which is 323 divided by 293 times 2.6, and this gives us 2.87 approximately bar. So you see that indeed the pressure inside the tires increases when you drive for a certain time and increases if your tire gets warm. Okay, so that's why managing tires like in F1, etc., is not always so easy, because the properties of the tires change. with the temperature. Okay, that's also the reason why in F1 they always do before starting a tour to warm up the tires. You saw that if you watch F1. Okay, they do a tour to warm up the tire, and during these tours they do strange things with the car to increase friction so that the tires get warm and so that they have the characteristics which are requested for the race. Are you amazed? Tell me you're amazed. Tell me you're interested. Or tell me, I don't know, you don't give a shit, but say something. Okay. Okay, listen, the next exercise is exactly the same type, so there's no point doing it. Okay, this concludes the course on heat and concludes the course of 200 DF. And so if you still have questions, I will be happy to answer it. Otherwise, I will see you next year probably. Unless some of you want support, I will put a message on all my classes to say if some student wants support, I can come to the school and help you, etc. Okay? Okay. Any questions? No. Okay. Okay, I will put the video online for those who were not here, and I wish you a nice evening and a nice summer if we don't meet again, and we will meet at least in the corridors next year. Okay? Okay. Bye. Bye bye. Have a nice evening. Bye bye. Bye.